Hey guys, today I'm going to talk to you about nuclear chemistry that deals with these four types of nuclear decay and nuclear half-lives. So, we'll just start with alpha decay. Alpha decay is when a nucleus emits an alpha particle. So my example for this is curium-242 experiences alpha decay. Here's our equation. Here's our unknown element, and then here is helium-4. So let's go to the drawing board to figure this out. So to tell you, the top number represents the number of nucleons that this element possesses, and then the bottom number is the number of protons that it possesses. And when you're dealing with alpha decay, you always use helium-4. So when doing these kinds of problems, you have to make sure that the nucleons cancel each other out, which means that you have to make sure that there's the same number on each side, and that goes the same with the protons. So we'll use simple algebra to figure out this problem. So, like I said, you have to make sure the nucleons equal out. So you take 242 minus 4 equals 238. And then 96 minus 2 equals 94. So your answer is 238, 94. And that is plutonium. If you don't have a periodic table of the elements in front of you. So next we will go to beta decay. And beta decay is when an electron is ejected from a neutron, resulting in the neutron becoming a proton. And with beta decay, we have a little diagram right here and a equation to help you figure out any problems that you have. So my example for this is magnesium-28 emits a beta particle. And so here is our equation. Now, unlike alpha decay, you use an electron and not helium-4. But the math is pretty much the same. You just have to make sure that you cancel everything out, or that everything equals on each side. So what we did, 28 minus 0 equals 28. And then 12 plus 1, because that's a negative, so you have to have one more on this side to make sure that these balance, would be 13, because 12 plus 1 is 13. And if you don't have a periodic table of the elements in front of you, this is aluminum, because aluminum has 13 protons. So this is aluminum-28. Let's go on to our next one, which is positron emission. And positron emission is pretty much beta positive decay. That's another name for it. And this is when a high-speed positron is ejected from a proton, resulting in the proton becoming a neutron. And just like beta decay, we have a little equation right here to help you out. Here's our little positron inside the proton. Here's our neutron, and then there's our little itty-bitty positron right there. So my equation, or my example for you, is carbon-11 undergoes positron emission. And again, instead of using an electron, this is the positron, so it has a +1 charge. So, let's go to the drawing board. Okay, so again, we'll use simple algebra, and you have to make sure that the top numbers cancel out on each other's side, so they have to be the same. And then that's the same with the protons on the bottom. So 11 minus 0 would be 11, and then 6 minus 1 is 5. Again, simple algebra. And if you don't have a periodic table of the elements in front of you, this is boron. Boron 11, because boron has 5 protons. So that is positron emission. Alright, our last one is electron capture. And electron capture is when a proton absorbs an electron, resulting in the proton becoming a neutron. And so again, we have another little diagram and an equation to help you. There's our proton, there's our electron, and our resulting neutron. And so my example for you is vanadium-50 undergoes electron capture. So, let's go to the drawing board. So with this one, we again use simple algebra to figure out what our unknown is. So in this time, we're actually going to add everything. So 50 plus 0 is 50, And then 23 minus 1 is 22. Simple algebra. So again, we have to figure out in the periodic table of the elements what element has 22 protons. And this is titanium. And so our answer for this is titanium 50. So my last thing to talk about is nuclear half-life, and this is the time it takes for half of a radioactive sample of an isotope to decay. And you got to remember that this is always first order and never second order. Now, with harder half-life problems, these are two equations that you would normally use. However, in today's lecture, I am just going to use a simple problem just to wrap your minds around the idea of a nuclear half-life. So I'm going to figure out 1, 2, 3, and 4 days in which how much of a 14-gram sample of a carbon-11 is left. So we go to the drawing board and we start with our 14 grams, and we have to figure out 1, 2, 3, and 4 days of how much is left after each day. And it has a half-life of 2 days. So after 2 days, half of it will be gone, resulting in, as we know, 7 grams left. So the way we can do this is that if after 2 days we have 7, we know that that's pretty much a quarter every day that 14 grams has lost. So a quarter of 14 is 3.5. So 14 minus 3.5 is 10.5. Then we have 7. Then we have 3.5. And then we have 0. So after 4 days, all this sample is gone. So this is just quarters. Now with other problems, you may have a half-life of 4 days, you may have a 14-gram sample, and it may be a little bit more difficult to solve. But this is just a generic problem in which all you had to do was, using the half-life, find how many grams are left after each day. And that is pretty much the basics of nuclear chem. Thanks for watching.